Hello everyone, this is Dr. Hopkins with our last video in our discussion of acid-base chemistry, or Bronsted-Lowry acid-base chemistry in 106. And today we're going to do a short one on multiprotics titration curves. And so here we start with a kind of sketch, I don't know if you want to call it a cartoon, of a titration curve where we have a diprotic acid or polyprotic acid. But if we could have 3, 4, it doesn't really matter. Titrating with a strong base. So you just simply get multiple titration curves. So we get the same kind of form. We start with the acid before we start adding base, and then we titrate into a buffer region where we've got both the acid and its conjugate base. And eventually we get to the first equivalence point where we have completely reacted the OH minus with all of the first proton. Then we start reacting with the second proton. It does it sequentially. It doesn't do them two at a time. It does all of the first proton, then all of the second proton. And so we go through a second buffer region where we have the conjugate acid, or the acid in the conjugate base for the second proton, and we eventually get to a second equivalence point. And once we've gotten past the final equivalence point, we just have excess strong base at a high pH. So you would get some kind of curve like this. If you had a triprotic, you might have 3 equivalence points and 3 buffer regions, but you would have something that looks similar to that. So, for example, if we had 0.1 molar carbonic acid, 10 milliliters of it, we'll start with that. We got a Ka of 4.3 times 10 to the minus 7, a Ka2 of 4.7 times 10 to the minus 11, and we're going to titrate it with our standard 0.1 molar sodium hydroxide. Now, we're not going to go through all of the kind of math and the ice tables because we already know how to do that. We've done that multiple times. We did that multiple times before. Then we reviewed it when we've done our titration curves. So I'm going to let you do that step later on, but let's kind of think about this conceptually. So what volume would be required to get to the first equivalence point? So if we had 10 milliliters of 0.1 molar acid and we have 0.1 molar base, we just need 10 milliliters because it's moles of acid to moles of base. That's for the first proton. So then the question is, what is our species that's left? And it's HCO3 minus. It's the conjugate base of the carbonic acid. So then what volume would be required to get to the second equivalence point? Okay, now it depends on how you frame this, but now we have to get rid of 2 protons to get to the second equivalence point. So it would be 20 milliliters, or basically an additional 10 milliliters past the first. So if we get 10 milliliters to get to HCO3 minus, and then 10 more milliliters for a total of 20 to get to CO3 2 minus. And that's what we would have at that equivalence point. And then the other feature is that we have 2 buffer regions. And, if we think about this, these are 2 buffers, so this would work as a buffer over 2 different pH ranges. So what are those pH ranges? And they'd be around the pKa, so the 2 pKa's. So the first pKa is around 6, so between 5 and 7. And then the second pKa is around 10, so between 9 and 11. So plus or minus 1 is typically where it acts as a buffer. But those would be our buffer regions, and you would see kind of a region where it doesn't really change pH very much as we're adding hydroxide. And so that would be a feature of these titration curves, these polyprotic or multiprotic titration curves. So the end of this, we've got titration curves of the polyprotic acid. Could have a polyprotic base, but we're not showing it. They're going to have multiple equivalence points and multiple buffer regions. And once again, we could still go through the process of calculating the pH at each point. We just have to be very meticulous in reacting, figuring out what moles, what's left, what's the strongest acid or base left. Is it an ice table? Is it a strong acid or a strong base? And then figure that out. The only trick is that when you have a polyprotic, sometimes it's a little hard to determine whether your conjugate base is better as an acid or as a base. So until next time.